Jim Gattaker. I'll chair this morning. The first speaker is Professor Gianluigi Rozza. Close enough. Professor of Numerical Analysis and Scientific Computing at the International School for Advanced Studies in Trieste, Italy. Research interests include numerical analysis, scientific computing, reduced order models and methods, computational fluid dynamics in aero, naval, and mechanical engineering, hemodynamics and environmental fluid dynamics. He'll deliver the talk. I have to double check that the things didn't change too much. Weighted reduced order methods and parametrized PDEs with random inputs. Gianluigi.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen. And before starting, I would like to address special thanks to the organizer for this special semester at Isaac Newton Institute, Catherine Powell, Max Goldsburger, Henry Wynne, and Peter Challenor. And I would like also to thank my co-organizer for the workshop number 3. So Elizabeth Ullman, James Gattiger, Francisco Alejandro Diaz de la O. And I would like to address two special thanks. One is for Catherine Powell for being always very responsive and taking care of several issues and to support us a lot. And another very special thanks is for Elizabeth Ullman, who was a very special supporter and not only assist but a special co-organizer in taking care of so many of the logistics issues. So thanks a lot for this. Today I'm going to introduce some of the topics that I am carrying out in my group at the International School for Advanced Studies, SISSA, and especially in collaboration with Francesco Ballarin, who is a postdoc of mine, and 3 students, Davide Torlo, who is now at the University of Zurich, Luca Venturi, who is now at Curran Institute for Mathematical Sciences in New York City, and Maria Strazzullo, who is still a PhD student at SISSA. I would like to provide you at the beginning an overview of our research activity. Then I will focus for the most part of my talk on the weighted reduced order method with some current topics. And then I would like also to address an example of optimal flow control with data assimilation, so a more classical uncertainty quantification problem for my group. As you know, the leading motivation for the development of reduced order method has been also the growth of important computational sciences and engineering and simulation-based science. At the current state of the art, let's say that the interest is moving towards especially multi-physics problem and also to problems characterized by multiple spatial and temporal scales. And since we are also collaborating with several industrial and clinical research partners, from them we have a growing demand of efficient computational tool for many query real-time computation, so a repetitive computational environment, as well as the demand of having parametric computing and the capability to increase in the mathematical models for complex systems also some uncertain scenarios. And another thing that I would like to add to this framework is also the fact that we are trying to carry out a better exploitation in terms of computational collaboration between high-performance computing and reduced order method. So we have not to see the reduced order method as a competitor, but mostly a collaborator for scientific computing. So also a better combination of what is full high order with respect to what is reduced order. This is my group at SISSA, so mostly we focus on computational fluid dynamics, but today we are not seeing a lot of computational fluid dynamics, but we are seeing more some methodological example at the beginning, an example of environmental flows at the end. I would like to underline that reduced order methods are at the moment are not suited completely for addressing real life, real world and complex industrial problems. There are still several limitations at the state of the art, and one of the goals is try to increase these capabilities in order to address more demanding application, not only in industrial setting, but also in what is medical fields and in a more general applied science setting. Our group is carrying out numerical development, so we are numerical analysts, and our special emphasis in any case is into a better exploitation of computational science and engineering. I mentioned computational fluid dynamics as one of the central topics, the central physics of interest for us, but of course we are addressing multiphysics also, so the combination of fluid with the structure, with the thermal field, with porous media, for example, and so our interest is to go into a coupled setting. There are several potential applications. I just mentioned few fields of application in engineering, aeronautics, mechanical engineering, and what is related with naval, offshore, nautical fields, but also wind, sport engineering, biomedical application, and especially cardiovascular surgery. I would like to provide also in this overview a sort of paradigm of what we mean with the combination of high-performance computing and reduced order methods, and which are the instruments, the tools that we can use. So our goal, our dream, is to be able to guarantee real-time computing, but also visualization, and we use this offline computational paradigm. So trying to combine high-performance computing capabilities, supercomputers, which usually are in research centers, so we say that they are science-driven, and what is reduced order method, performed into an online step. This online computational step is carried out on a desktop, on a laptop, but also on modern devices like tablets or smartphones. So the capability of combining these two different technologies. Of course, the one online are more driven by industrial needs, application needs. So one of the possibilities is to be able to export better numerical simulation, scientific computing in fields, in places where at the moment there is still little exploitation, because it's not easy to have always available a supercomputer into a research center or an institute. And our first action has been the one devoting our attention to the development of some open source tools in terms of software. So there are, I am proposing here two different initiatives. One is more research oriented, is more professional, is related with industrial and biomedical application, and the call of this, the name of this initiative is Ithaca. Ithaca is in real-time, highly advanced computational application, and this is an open source software implementing all reduced order algorithms and methodologies with interface with the most spread and known open source software for full order discretization. So there is a port for OpenFOAM if you are an expert in finite volume simulation, Nectar if you are an expert in spectral element methods, or Phenis if you are an expert in finite element, or LibMesh for finite element as well. And this is one of the open source initiative, and you can already download some release at this web address. The other one is called Herbenix, and Herbenix is a computational tool based on Python, combining Phenis project. Phenis project is a very well-known finite element library, open source, kept and developed also by Simula, National Simula Laboratory in Oslo, Norway. And the idea is that this is fitting and suited for newcomers in a reduced order methods community, so users which are non-expert, and also we are using these for academic training activities during classes. I would like just to provide you an overview of what we mean with the reduced order method before going in more details. So I would like to say that this is an old idea facing difficult problems, and in the same years we had the development of a reduced basis method as a continuation method in nonlinear structural mechanics, and in the same years, proper orthogonal decomposition was proposed to model transient and turbulent flows. At that time, extensive scientific computing was still a dream, and the problem that these two methodologies were facing and addressing were very, very complex. So other methodologies, of course, in the reduced order setting were proposed later, and I would like to mention, for example, a proper generalized decomposition. Maybe we will know more in the subsequent talks, and also hierarchical model reduction. But I would like to say that what I'm presenting today, and also I think also in many other talks today and tomorrow, is based on a pioneering activity in the 80s by several people who started to address a numerical analysis approach for this methodology. This methodology was then reproposed in 2000 with several new ideas, reinventing new ideas and recasting them into new paradigms. So several groups all over the world, especially in Europe and in North America. And I would like to mention the fact that the first mini symposia on reduced order methods, which now are an important component of some SIAM conference, for example, in computational science and engineering, were in 2001 into a mini symposium into ICOSOM, International Congress on Spectral High Order Methods, and in Uppsala, in Sweden, and then in Providence in 2004. And the organizers were Yvonne Madet, Université Paris-6, Jacques Lyon's laboratoire, and Anthony Patera from MIT. So this is a relatively young age for this method. After that, I would like to mention that starting in 2010, even more several groups are addressing methodological development and application of reduced basis method. So I'm not counting my generation, and this list is is a non-complete list, but from generation before mine. And I would like to say that now the specialization of several groups is very important in some specific topics and in some specific algorithms. I would like again to address the fact that our need was also the better exploitation of what is a parallel computing, high performance computing in the offline setting combined with reduced order methods. So just to give you a very brief outline of the methodology, I would like to start saying that the calligraphic N is referring to a truth approximation, so a classical discretization, which is called full order. And we can have this one using finite element, finite volume, finite difference, and spectral element method. So this is what we would like to accelerate. On the other side, we have the reduced order model, we indicated here with the PDEs capital N, and this is the accelerator. So we have input parameters. Now the input can represent the shape of a domain or a physical quantity, also non-dimensional coefficient, but later for us will be some random inputs. And the parametrized PDEs here are represented by this abstract operator, the calligraphic A, and we have the problem at three different levels: the exact one, the full order one, where maybe you are already somehow expert with, for example, finite element, and the reduced order one. But the structure is the same. The difference is coming from the dimension of these matrices that we are dealing with. Of course, we can be interested in extracting U. U is our state solution, but also into a related quantity. So, for example, an output indicated here with S, always at full order or at reduced order. Sometimes the reduced order solution are also indicated as surrogate. So the idea is to have an input-output black box, an input-output evaluator, to go from mu to the output solution. Here, just to go more into a practical point of view, and just for this overview, we were talking about offline and online computational steps. The offline part now means to proper sample the basis function, so it means that we have to solve our problem for some value of the parameter. And the solution of this computation are going into this matrix. This matrix is called snapshot matrix, calligraphic Z. And in the column of this matrix, we have the solution for the selected value of the parameter. Once we are done with this, and then I will show some idea about the sampling, also with random input, we have an online computational step. The online computational step is based on two assumptions. The first one is that we can simplify our operator into a sum of a product between a parameter dependent part and a parameter independent part. So a matrix which is not depending on the parameter, and a function which is playing the role of a coefficient for our component of the operator. And of course, to be able to do this, we have some assumption, and we have to recover also some properties in case they are not available. And this is the decomposition that we see here in green. But the other important one, which is just the main idea, and this is taken more from the engineering point of view, is the fact that these are our original matrices, the full order one, and we can have this reduction in terms of dimension for columns and rows, thanks to the fact that we are pre-multiplying and post-multiplying our full order matrix with the snapshot matrix. So this is the main idea, the kernel idea of what we are doing. So the ideas are simple and they are not new. We are just trying to recast these in proper needs for application or setting. Of course, there are several issues about stability of the method, the computation of error bounds, efficient parametrization to be able to have this operator in this way, and sampling. And today I mostly give you some assumption on how to use these methods for an efficient sampling with the random input. But I would like to underline the fact that this methodology is also fitted for some challenges in uncertainty quantification. So if in 90 or at the beginning of 2000 we were mostly addressing attention on simulation or control and optimization, now we can address better our attention to some proper computational reduction technique for real-time control optimization, or more in general to inverse problems. And for inverse problem, I do not mean only control problem, shape optimization, but also some problems that are including data assimilation, parameter estimation, also risk analysis. And this is something important because we can better bridge the mathematical model that we are creating with the reality, thanks to this the incorporation of real data, and we can improve also applicability scenario. So I think that numerical analysis is in great need of real data, and also in being able to perform some quantification of uncertainty. I would like just to say you that if you are interested into a review paper at the state of the art for reduced order methods with uncertainty quantification, there is a recent one, a review paper on SIAM Journal Uncertainty Quantification with Chen and Alfio Quarteroni. Now I have to acknowledge many collaborators on these topics, also at SISSA and also at the international level, and I would like to provide you the main example for today. So how to introduce a weighted reduced order methods approach for parametric PDEs with some random input. Here, this problem is already quite complex because this is an advection diffusion problem, and you have this front propagating at a different angle, and the angle of this propagation is one of the parameters, for example. So we have also the boundary layer that are here, and here. And this is just an example of a parametric solution. So for now, parametrized PDEs means at the moment an elliptic PDEs. For parameters, we mean some random input. We are interested in evaluating some statistics over the state solution U, for example, the expected solution. And we would like to use a reduced order method to accelerate Monte Carlo method. And now the questions are how to weight the solution during the construction of the reduced order method, and how to sample the parameter space during the construction of this reduced order method. For a weighted reduced order method, I would like to, the first paper addressing this issue was one on SIAM Numerical Analysis 2013 with Chen, and more recently we have an update with Davide Torlo. And the other proposal is to use a weighted proper orthogonal decomposition method, and this, for example, you can find something in collaboration with Luca Venturi. For us, since we are interested in computational fluid dynamics, this means try also to combine this setting that I'm going to introduce with some more classical numerical stabilization technique based on SUPG, stream upwind Petrov-Galerki. So we will have a physical stabilization on one side, which is affecting our problem, and then a problem of weighting and sampling proper the construction of the reduced order method. Just to provide you some notation with omega, we have our subset of RD, so this is a physical domain. Then we have the probability space. A is the set of possible outcomes event, the calligraphic S as the sigma algebra of the event, and P the probability measure of the event. So our parameter mu is the random vector now from AF to calligraphic D and B, and D is just a compact set in the parameter space as a subset of RP. P is the cardinality of our parametrization. And of course our mu, now omega, we can say this is just an independent, identically distributed, continuous random variable. And for B is our classical Borel sigma algebra. With V we indicate the functional space, so which is contained and is containing H10, H1. And with S we indicate the product space between the L2 events and the functional space V. Our attention is on this equation. This equation is an advection diffusion stochastic equation. You see the parameter mu acting on the diffusion coefficient in these transport terms, and also maybe in the right hand side. Then you have these diffusion terms and the transport terms. So our idea is that the solution used now is a random field bounded somehow in the norms of S. So the classical greedy algorithm used to select and to build our reduced basis method is reported here. So we have a discretization of our parameter space. This is a training set. We can take arbitrarily the first mu1 selected. At the beginning the sample is empty and also the space is still empty. And then, given a maximum dimension of our space, we can perform several PDEs solves such that we are able to get each time the solution for the selected value of the parameter. This solution, the selected value, is appended to the sample set and to the space, and of course the next parameter will be selected in the worst case scenario, so where we are maximizing our error bounds delta n. For us, delta n is a surrogate error bound for this real error in the reduced basis. So this is based usually on the residual and on stability factor. But at the moment, take it as something that there is a tool to compute this. If we want to weight this reduced order method, so the idea is that we are interested in having this quantity, so the expectation of the error of the reduced basis formulation, and from the probability space we go in the parameter space, and so we introduce this rho mu. Rho mu is the probability density distribution, and if we are replacing this quantity with the error bound, we have this inequality. This is for us our new error bound for this kind of weighted approach in the reduced order method, and our weight W is just the square root of rho. And our new error bound is going to be weighted. So we have the deterministic error bound based on the residual and stability factor, and we add this quantity under square root. So the weighted greedy is exactly as before, but not only we have to properly sample Xi-train, but we replace the error bound with this new weighted error bound thanks to the probability density function. If we want to go to a more general approach, maybe you are more familiar with the proper orthogonal decomposition, we know that in this case we have to compute all the solution for the selected value of the parameter in the discretization of our Xi-train. So the idea is that here we have to put a more important investment in terms of scientific computing to the solution of this U for all the value of the parameter in Xi-train that we have discretized. And after we are done with this, we can build the correlation matrix C. So C is of dimension capital N times capital N, which is the cardinality of the Xi-train. As this is the classical correlation matrix for the POD. Then we have to extract the eigenvalue of C. We have to sort them into a decreasing order, and we can truncate the selection, some of them, just retaining the ones that, for example, are larger in the sum than a tolerance. So this is the classical POD. What can be done in terms of weighting PODs is this kind of approach. We know that the POD is minimizing this kind of error, so a square V error, usually is an L2 error, between the rebuilt of the reducer basis solution and the exact one. What we can do is to introduce a weight here. And this weight is also influencing the construction of our method, because instead of dealing with the correlation matrix, we can deal with the weighted correlation matrix. So W is just the matrix where in the diagonal element we have the weights for the value of the parameter mu I already used to discretize our parameter space. So this is the proposal for a weighted POD. The algorithm is always the same in terms of, so the computational load is the same. What is different is that in this case we have just to work on this weighted correlation matrix and computing the eigenvalue of this weighted correlation matrix, and then doing the truncation on these CW matrices. Now we can have also other options. Some of them, for example, we can introduce as a weight directly the probability density function, and using as parameter sampling a uniform distribution. So this is a classical uniform Monte Carlo quadrature approach for this square error norm of the reduced basis approximation. Another possibility is that we put double U mu equal to 1, and we use for mu1 a Monte Carlo distribution of this, not a uniform one. And so we can compare and we can understand how with the reduced order method we can accelerate this Monte Carlo approach. A more general approach, so with a more general quadrature rule, is that we may think that for every integral function f from the parameter to real number, we can use this kind of a quadrature rule, where you have as x 1 to m the nodes of the quadrature, and with omega 1 m the respective weights. And this is resulting in this more general formulation, where we have a proper selection of the nodes, we have the density, the probability density function evaluated in the nodes, and then you have also the weights omega 1. So, of course, this can contain the former approaches as a particular case, and the idea now, the motivation to this approach is that we have the possibility to proper sampling the parameter space, so our quadrature nodes, and at the same time we have also the possibility to weight well our approach with the proper weights of the quadrature rule or the probability density function. So this is a generalization, and the test that we would like to introduce is related with a very simple thermal block. We have 9 parameters with 9 different conductivity in 9 different zones. The distribution of each of these conductivity coefficient here, this is a very simple Poisson problem. The parameter is playing here as the conductivity in each subdomain, and the formulation of this is a weak formulation of a Poisson problem, and the coefficient, the conductivity are distributed well, they are rescaled, but this is the beta distribution of this parameter in terms of alpha and beta. So you can see this is a wider distribution and this is a narrower distribution. The approaches that I would like to compare are related with the standard reduced basis approach, and then the weighted. One is with a uniform distribution and one is with the Monte Carlo distribution. And then we have, in terms of POD, we have the standard one, or the one with the Monte Carlo, then a uniform Monte Carlo but using a probability density function, and as a more general quadrature rule we can use the Gauss-Jacobi and the Gauss-Legendre, just as an example. And here we have the convergence of these different greedy algorithms. So you have the increase of the dimension of the reduced basis method and the error which is giving us the convergence. We can see that the weighted approaches for two different distributions are better, especially the one with the weighted with the Monte Carlo distribution. This is the standard greedy, and in general, using a weighted greedy with a uniform distribution, we may have an improvement here, but not here. So this is not maybe the one to be used. If we go now to compare some POD versus a weighted POD, we can see that in general weighting also the POD is better, because in red we have the standard one, and then the weighted approaches are providing better performances, and the Monte Carlo POD with the proper distribution is better usually than the other one. And if the distribution is quite narrow, like in this case, you can see that the difference is even more evident than here. If now we go to a more general weighted approach for the POD, using also some more specific quadrature rule like Gauss-Jacobi, and we compare with the distribution of Monte Carlo, we can see again that compared with the standard POD in red, we are performing better. But the difference between the Monte Carlo weighted POD with the distribution and a Gauss-Jacobi is not that much. But we can use this in order to improve some computational performances offline. So we can try to introduce the idea of having some sparse grid in the sampling, and instead of using this tensor product for Gauss-Jacobi. And this is what we are going to propose now here. So we have a comparison between Gauss-Jacobi with a quadrature rule based on tensor product, and also the fact that we can use an approach based on sparse Gauss-Jacobi. For example, using a sparse Smolyak quadrature rule of order, this is order 11. And you can see that the sparsity is a little bit better compared with the classical one, but in terms of computation, this can be seen as an equivalent. What is important is the dimension of the offline Xi-train. You can see that from more than 500 we have 180. So we are able to save more than 60% of computational cost in the offline part. So this is something that should be taken into consideration for this kind of problem. If now we want to go more generally on some advection diffusion problems, so with also a transport dominated problem, as you know, we have to stabilize. So the idea is that we can have a regular stabilization in the offline and online setting, or otherwise an offline only stabilization. The offline only stabilization, it means that we are not using a consistent method between offline and online part, and this is good for low Peclet number. Peclet is the dimensional coefficient indicating us how much the problem is transport dominated. So for higher Peclet number, the stabilization is an issue in order to guarantee the fact that in each cell we have to guarantee low Peclet number. So my test is based on a Gratz flow. We have this flow, this thermal flow entering, this is the inflow, this is the outflow. We have this cold zone, and then we are heating this wall, so the temperature is higher, and the parameter in this case are represented by the Peclet number itself and the geometry of this channel, this length. And of course also in this case we have this beta distribution for the random input, and you can see that the Peclet number is going from 10 to 10.6. So the range of variation of the Peclet number is considered huge. A former approach was, deterministic approach was provided by, in a paper on Kamame with Paolo Pacciarini, but here you can see for different Peclet number, the different physical behavior of the thermal flow and the temperature distribution. Here we don't have any boundary layer. Here we have two boundary layers that are somehow intersecting, and here we have very thin boundary layer, and so this is a very high gradient zone. So physics is very different. And what is going to happen? If we are not stabilizing, we have this consistency problem. So the offline only stabilization, we don't have a lot of accuracy, and if we compare the true error with the error bounds, we have always the fact that in any case our error are below than the error bound that are in any case providing us something with an effectivity greater than 1. But for a large Peclet number, we suggest that it's better to stabilize also for this kind of problem. So here we have a comparison with offline-online stabilization using a standard greedy algorithm with an uniform Monte Carlo. Then we have a standard greedy algorithm but with a proper beta distribution for Monte Carlo. And then we have the weighted approach in green, which is better than the one not weighted. And if we have also a weighted greedy and a proper Monte Carlo distribution, we have the red performances. So you can see that from the black to the red one, we have some improvement that are fitting better our greedy and sampling approaches to this kind of problem. This is what can happen if we are not using the proper stabilization. So if we go just with the offline stabilization, we are in the blue zone, and we are in the red zone, so we can have a better accuracy doing an offline-online stabilization. This is important because for higher Peclet number, so this is the logarithmic of the Peclet number, it's important that we use also an online stabilization combined with the proper sampling for the random input. And just for the low Peclet number, we can say that things are going well. And so here it's important to combine the proper weighting and sampling based on the probability density function, having a random input, and at the same time taking into account that you have some physics due to the Peclet number that is affecting our problem, and we need also this kind of stabilization. So the idea could be, if you have this distribution of the parameter, this is the logarithmic of the Peclet. What we can test is to move this vertical bar from the left to the right in order to combine some different situation between the stabilization. So we can decide to weight also our stabilization, and the idea is reported here. So if we are increasing the percentage of non-stabilized non-stabilization terms, we can see that the error will worse according the increase of our Peclet number. But this is not sufficient, because if you go on this direction with this vertical approach, you can see that we are just catching a better physics, but we are not taking into account that, for example, here the probability is going again down. So we should use a different approach. And the different approach is a combination between this and this one, where we have an horizontal bar. If we are moving this horizontal bar, we can take better into account the fact that here the distribution is more important than in this zone and in this zone. But at the same time, if we combine this with a vertical approach, like this one, we can take into account that this zone, even if we have a low distribution, we have important physical phenomena that should be taken into account. So the idea is the combination of the two, and this is a selective online stabilization. We can deactivate some zone of destabilization where physics is not important, or where the probability density function is not providing any important snapshot. So the idea is to go with adaptivity and be more selective. To wrap up, I would like to just to say that the approach that I propose here is suited for stochastic parametric PDEs, and our reduced order method that we have introduced here could be performed in two ways. Or we are going to weight the reduced basis method, or we are going to weight a proper orthogonal decomposition approach. In any case, weighting is important, but is not sufficient. A proper sampling is very important, and so the final outcome is that we should go to possibly sparse quadrature rules to have a good performance, and at the same time to have a good offline computational savings. When we have some physics, which is quite important, like in the transport-dominated problem, we have also to take into account stabilization, and we have to combine this stabilization not only to the weight and to the distribution, but also to the instability arising from the numerical point of view due to the, for example, in this case, for the Peclet number. And I would like also to mention the fact that we are going to do this problem also in fluid dynamics. Shafkat Ali is doing this in his PhD, and here we have the main idea of what we are doing. So these are more computational fluid dynamics problem than the transport one that I introduced before, and you can see that the idea is again to introduce offline-online stabilization technique based on stream up in Petrov-Galerkin for the Stokes and Navier-Stokes equation, so nonlinear fluid dynamics equation. And another possibility is to also use a variational multi-scale method into a reduced order setting with offline-online computational decomposition. And also we are interested in having some tools able to model some moderate turbulence, for example using some Smagorinsky model. And this is for more important industrial and cardiovascular application. I stop here because otherwise I go over time, and I would like to thank you for your attention.
When you mentioned that you can do the online parameterization only, for example, for areas where the physics is important.
Yes.
How actually? So do you know beforehand where the? Obviously, for some cases, it's easy to say where there's something interesting happening. If it's a flow past a certain body, you know that behind is something important. But can you do it adaptively? Can you, while you're running your simulation, can you then adapt where something important is happening?
We are trying to do this, but I have to say that the approach that I was using, since it was very academic one, we know that the Peclet number is playing an important role in physics. But your question is very important, because, for example, sometimes in more complex nonlinear problem in fluid dynamics, we have bifurcation. So for the same value of the parameter, we lose the uniqueness of the solution. We may have 2, 3, or even more solutions. This is also a case that is also well known in nonlinear structural mechanics. So in this case, we should compare a deterministic knowledge before of what is happening, and then moving to this approach. Unluckily, otherwise we risk to not to be able to. So the human brain is not it could not be replaced, but an automatic algorithm combining proper sampling and weighting, when we have also physics affecting our problem in terms of loss of uniqueness of the solution, for example, or instability.
Do you need the slides, or can we switch over?
What?
Do you need to ask about slides, or can we switch computers over while you're...
No, I wasn't questioned to the talk.
Yes, do you need to refer to his slides?
Not really.
Okay. We'll switch over if you can
Okay.
do the question.